Good day, everybody, and well, we are back together again. So today we are going to be looking at. I know that you guys are writing the prelims. All right, some of you may have written physics, some of you are yet to write. But I thought that for those of you that may be writing, we are going to be looking at physical science, which is paper 1. All right, I'm going to be looking at 3 sections. Number 1, I'm going to look at Newton's laws. There's a very interesting question paper that I have. It's a pre-trial from KZN. The second one I'm going to look at is work, energy, and power. I tried that question before, guys, and it showed me flames, but I'm going to try it. I'm going to do it with you. And then the last part will be electricity. I think those are the 3 sections that I'd want for us to spend a little bit of time and looking at them. So please, for those of you that as yet have not subscribed, please just hit that subscribe button. And please note, on Saturday we are having a workshop, right? For those of you that may be struggling with the chemistry, that have particular specific questions on chemistry, you're more than welcome to join that workshop. It's only 200 rands, it's 4 hours. In fact, I think we extended it to 6 hours. Right, and I think that's really affordable. So please do join us for that workshop. It's on paper 2. So I will be looking at chemical equilibrium. I will be looking at acids and bases, which is another one that I was asked to do. And I will be looking at organic chemistry and rates of reactions. Those are the 4 sections that I will be looking at. So if you are ready, I'm ready. Let's get right into it. Okay, so as I said, I'm looking at this pre-trial and I'm going to be starting on Newton's laws. All right, let's get into it. So question number 2. Okay, there it is. Okay, so they say to us, we've got a group of learners that design a device that consists of a light ball on a string hanging from the roof of a cargo truck. They say this device is used to determine the acceleration of the truck when the truck is stationary or moving at a constant speed, right? The ball will hang straight down. Now that makes sense. If the truck is stationary, it means that when you're looking at the ball will just be hanging straight, it won't be moving. But when it is undergoing a constant acceleration, now you can imagine, because of that, the law of inertia, right? So in this case, the moment that the truck starts moving, then the ball will swing the opposite direction. They say the ball hangs down an angle theta as shown in the diagram. All right, now let's go right into it. So they say draw a free body diagram of all forces acting on the ball. So what is that going to look like? Okay, so we're going to have the tension on the string. Okay, and we are also going to have, so that's tension on string, and please remember to label in full. Okay, so tension on string as well as gravitational force. So those are the only 2 forces that are acting, right? You can say gravitational force, or you can say the weight of the object. It's neither here nor there. All right, so the next question, so it's out of 2 marks, by the way, so that tells you that will be the mark allocation. The mark allocation rather shows you the amount of forces that you are meant to have. All right, I'm just gonna switch this guy off, sorry about that. Right, they say in this case the mass of the ball is 50 grams and the angle theta is 18 degrees. They say calculate the horizontal force on the ball. Now, I want you to keep in mind that when we're looking at the horizontal force, remember that because the tension on the string is now diagonal like that, okay? So it's going to cause the force on the, the forces acting on the string, on the ball, right, to have 2 components. Okay, maybe let me just use a different color. So you're gonna have a vertical component, a horizontal component. I don't know why this thing is behaving like this today. Right, you're going to have a horizontal component like this, and you're going to also have a vertical component. Okay, so how do I find that? They said our angle is 18 degrees. Okay, but remember, for our vertical component, we're going to have, in this case, the value of, the gravitational force, right? So that is the one that is countering the weight of this guy. So in that case, I know that my weight, okay, my force of gravity, that's mass times gravitational acceleration, that's going to be 50 grams. Now remember, in physics we work with kilograms, so I'm going to say 50 divided by 1,000 to make it kilograms. So that will be 0.05. That's 50 divided by 1,000 multiplied by 9.8. Okay, so let's get that quickly. That's times 9.8. I get 0.49. Okay, so that's going to be the weight, right? But remember, what am I looking for? I'm looking for the horizontal force, right? Which is this guy, Fx, over here. Right, so where is it on this triangle? So if I want to draw this triangle to be big enough so that you can see it, so it's going to look like that. That's the tension. Okay, and there's my horizontal force over there. Right, I've got my angle 18 degrees. I'm looking for the side that is opposite. And which side do I have? I've got the adjacent side. Okay, so I'm given that my weight, or rather I calculated my weight to be 0.49 newtons. Right, so which means I can now say the 10 of 18, remember 10 is opposite over adjacent. The 10 of 18 degrees will be opposite. That's going to be Fx divided by my adjacent side, which is my weight. So that's 0.49. And so if I am going to cross multiply there, I'm going to eventually have Fx being equal to 0.49 multiplied by the 10 of 18 degrees. Okay, 0.49 multiplied by the 10 of 18. Okay, and I get 0.159. I'm going to say 0.16 newtons. Right, that is my horizontal force. Okay, so that is what we are going to get there. And then they say to us, calculate the magnitude of the acceleration of the truck. So remember, when we're looking at Newton's laws, we say that the body accelerates in the direction of the resultant force. So in this case, our horizontal force is the one that causes the horizontal acceleration. So which means if we say F net is equal to MA, that is going to be F net is 0.16. You remember that horizontal force is what we found. Right, our mass is 0.05 times the acceleration, and so we divide both sides by 0.05. Okay, right, so I'm going to say that value divided by 0.05, I get 3.18. Okay, so that's 3.18 meters per second squared. And that is how we are going to go about that question. All right, so please remember to just revise your Newton's laws, guys. It is very important for us to look at Newton's laws because it does carry quite a bit of weight. So let's look at the next one. They say to us we've got A and B below, which are two identical blocks, each with a mass of 5 kilograms, joined together by a light inextensible string. They say the blocks are being pulled with a force of 65 newtons at an angle of 40 degrees to the horizontal. The two blocks accelerate to the right at an acceleration of 2.17 meters per second squared. So remember, we know our acceleration. and they're telling us this is accelerating to the right at 2.17 meters per second squared. Right, and the tension on the rope, in the rope, is 26 newtons. Right, now they say to us, calculate the frictional force on each block. So let's consider each block. Let's look at let's look at block A first. Okay, what are the forces acting on block A? I'm going to have the tension, right? So block A would be this guy here, right? I've got tension, which is 26 newtons, right? This is the one that's causing block A to move, to accelerate at 2.17. And I've got the frictional force, which is opposing. Okay, I'm going to say kinetic friction there. And of course, we've got the normal force, if you don't mind. I don't need those, the normal force as well as gravitational force, because I'm only considering the horizontal acceleration of this guy. So let's look at it quickly. So F net is equal to MA. Sorry, I should have mentioned that this is for body A. Right, F net. Remember, we always consider the direction of motion as being positive. So to the right will be positive. So this will be tension minus frictional force or kinetic friction. This is MA. My tension is 26. I'm looking for frictional force. This is going to be 5 kilograms multiplied by acceleration is 2.17. Remember, you are given that. It's accelerating in the positive direction. Okay, so let's look for friction. So if I take friction to the side and I take that product to the other side, I end up with 26. Okay, let's do this. So that's going to be 26 minus 5 times 2.17. And I get 15.15 newtons. All right, so this is the frictional force on body A. All right, and then we move on to B. What does B look like? Now remember, we're pulling this guy with a force that is acting at an angle of 40 degrees. And that force, that applied force, was given to us. They said it's 65 newtons. Right, what other forces are acting on it? We know the frictional force. So that's friction, Fk on B. But we also know that we've got the tension. Okay, right, so those are the forces that are acting, well, horizontally. Of course, the applied force will still need to do something about it, right, to make it horizontal. So remember, so for this applied force, because it is not acting horizontally, we need to get a horizontal equivalent of this force. And how do we do that? Right, so if we were to take the horizontal equivalent, let's call it Fx, that means that this is on the, so if I were to think of this as a triangle, this is on the adjacent side, and we've got the hypotenuse. So which means adjacent over hypotenuse, that's cos. So which means to get Fx, it would simply be the hypotenuse, which is 65, multiplied by the cos of 40 degrees. Now, for those of you who may want to know, where does that come from? That comes from the fact that cos 40 is adjacent, which is Fx, divided by hypotenuse, which is 65. And if we cross multiply, this is cos 40 over 1. So you'll say Fx times 1, that's Fx, and 65 multiplied by cos 40, which is what we have over there. Right, if you don't mind, I'm going to leave it like that so that I don't round off. So which means we've effectively substituted that force with the one force, which is Fx, okay? Right. Now let's calculate. So which means F net is equal to MA. Again, so that means Fx minus the frictional force on B minus the tension. This is MA, let's substitute. So that would be 65 cos 40 minus friction. Remember, we're looking for frictional force, minus 26 newtons. This is equal to, the mass is 5 and the acceleration is 2.17. All right, so we're just going to do some gymnastics there mathematically, right? If we bring the friction to this side, going to take this guy to the other side, it becomes negative. So I've got 65 cos 40 minus 26 minus 5 times 2.17. Okay, I get a frictional force on B to be 12.94 newtons. Now I want you to note, guys, we got different values for friction, even though despite the fact that A and B had the same mass. Secondly, that they are on the same surface, right? But why is that? Okay, and which was, I think, the next question. That's what they asked us. They said, explain why the frictional forces on the blocks differ. Now I want you to note, guys, remember that the moment I look at B, right, the forces firstly that are acting on A are all horizontal, right, that were causing the acceleration. So meaning that vertically, the normal force would be equal to gravitational force. But look at what happens to B. B has got a force that is acting at an angle. So part of that force, what it is actually doing is that it is elevating block B a little bit, right? So that not all of the weight of the block is actually pressing against the surface, right? So think of block B being slightly lifted a little bit, so that in this case there's a lesser amount of the normal force. So they said explain why they differ. So I will say block B has a vertical component which reduces the normal force. Okay, so the vertical component reduces the normal force, making the frictional force on A less. Less than B, right? Less than that of B. Rather, less than that of A, right? So block B, I should have said, has a vertical component, okay, because of the applied force, all right? So it is making the normal force less than that of A, right? Guys, I hope that you understood that part, and please do practice Newton's laws very well, right? So that you get it right for the exams. I'm going to give you guys some advice at the end of this session, right, on how you should go around. You know, you should actually be looking at your prelim, right? Especially which questions, you know, you should really make sure that you capitalize on, where you should be scoring marks. All right, now let's look at the next question. They say to us, we've got a ball that is dropped from a height of 19.6 meters above the ground. It rebounds from the ground, reaching its original height. Okay, I want you to think about it. So we had a ball, there it is, it goes down, and then it goes back up again, and it goes where it started off. Now, before we even get into the question, What this simply means is that when the ball touched the ground, it did not lose energy. It did not lose kinetic energy. Right, if you know what these systems are called, we call this an inelastic system, right? So which means the collision with the ground, no man, did I say inelastic? Sorry. The collision with the ground is elastic, okay? Which means kinetic energy is conserved, okay? Right, so let's look at the questions. They say to us, oh no, I wasn't done reading the statement. They say ignore the contact time of the ball with the ground and the effects of air resistance. So the moment they say we ignore air resistance, we know that we are moving only under the influence of gravitational force. Right, now they say what is meant by a projectile, okay, in physics. Remember we say that it is an object that is given an initial velocity that moves under the influence of gravitational force only. Okay, so let's go to the next question. And guys, may I please just also advise, please learn your definitions. It is very important for you to know, I mean, definitions count about 10% of your final mark, right? So they definitely are worth it. Okay, so please learn them off by heart. Right, they say what is the total displacement of the ball? So imagine this, we started here, right? We come back to the same point, to the same position. Was there any change in position, right? On the final scheme of things? Absolutely not. So which means in this case, our total displacement would be 0 meters. All right, now let's go to the next point. They say use equations of motion only to calculate the time taken by the ball to raise up. Okay, I think they wanted to say to rise up the same height. Okay, so we want to know the time that would be taken to go back up again. But remember guys, what this simply means is that as the ball went down, right, whatever time it takes going down should be the same as the time it took going down, going up, right? Why is that? Because there was no change in displacement. There was no change in this case in terms of the displacement going down as well as the one going up. So the same time it will take the same time going up as well as coming down. Right, so what I'm going to do, I'm going to consider the direction. If you don't mind, I'm going to make this A. When it gets to the ground, I'm going to call that B. When it gets back, I'm going to call that C, right? So A and C are exactly the same point. So I'm going to consider motion going down because the same time it takes going down will be the time it takes going up. So A till B. Right. Now, very important, whenever you are doing vertical projectile motion, it's very important for you to be looking at, to choose a direction. So I'm going to consider direction up as positive. Now, once you've chosen up as positive, it means for any question that follows thereafter, you must make sure that you keep that, okay? So which means gravitational acceleration. Now remember, gravitational acceleration always acts vertically downwards. Whether an object is going up or is coming down, gravitational acceleration always acts vertically downwards. So which means for all the questions that we're going to do, we're going to take gravity as negative 9.8 meters per second squared, right? So let's look at it. So what is our initial velocity? Meaning the velocity at A. We started in this case from 0. They did say the ball is dropped, okay? Final velocity when we get to the ground is unknown. But gravitational acceleration, remember it's going down and we've chosen up as positive. So that's negative 9.8. The time is what we're looking for. And finally, the displacement. Right, how far will it be displaced downwards? That will be 19.6 meters. But we said up is positive. So where is it being displaced? It's being displaced downwards. So therefore, this is going to be negative. So remember, it's being displaced downwards. So that's negative 19.6. All right, now let's calculate. We are looking for the time taken. Okay, so we're looking for time. So in this case, what don't we have? Final velocity. So I'm going to use the only equation without final velocity, plus 1 over 2a delta t squared. For those of you that prefer s is equals to ut plus half a t squared, that's still okay. It's the same formula, right? So that's minus 19.8. Remember, initial velocity is 0. That makes that whole thing 0. That's half of negative 9.8 times delta t squared. Right, so that gives us minus 4.9 delta t squared, which is minus 19.8. So divide by negative 4.9. And we're going to take the square root. So let's do that quickly. Divided by 4.9. Okay, and of course that's the square root of, that's the square root of our answer. Okay, so we get delta t to be equal to 2.01 seconds. All right, so that's what we are going to get. So remember, it means it took 2.01 seconds going down. It means it took 2.01 seconds going up as well. Okay, right, now they say to us, calculate the velocity with which the ball leaves the ground after bouncing. Okay, after rebounding. So what are we looking for? We're looking for the velocity at B. Now remember, I can either look at the velocity when it got to B, or I can look at the velocity when it left B. Okay, because it will be the same, right? For the sake of space, I am going to look at, so that I make this land very well, because this is where some of the challenges in this section are. So I'm going to look at the motion going up. So I'm going to be from B to C, right? Now, going from B to C, remember we are going up this time. What is our initial velocity? Well, that's what we are trying to find, right? But what is our final velocity when we get to the maximum height? Remember, the ball is going to stop when it gets to that maximum height, so that's going to be 0. Gravitational acceleration, and this is where many of you tend to make mistakes. So remember, we chose down as positive. We chose up rather as positive, right? So consistently, gravitational acceleration does not change its direction, right? Whether an object is going down or whether an object is going up, gravity consistently pulls downwards. So gravitational acceleration will still be at minus 9.8. Why? Because we chose up as positive. Gravity still acts downwards, so that still continues to be negative 9.8. Okay, I know many of you would think, yeah, but now it's going up. Remember, gravity doesn't change its direction, okay? It's the ball that's changing its direction, so the velocity changes direction, but gravitational acceleration always remains downwards. Right, and the time that it took, remember we said it's the same time, so that's 2.01. And what about the displacement? So please keep in mind, guys, it is being displaced upwards, right? We said up is positive, so that's going to be positive 19.8 meters. Okay, right, so we're looking for final velocity. Which equation of motion are we going to use? We've got all the other information, so I'm going to make my life easier. I never miss an opportunity to use this first equation. It's the easiest, right? So this is going to be a final velocity 0. Initial velocity, that's going to be what we're looking for. G is minus 9.8, and the time is 2.01. All right, so let's find that. Times 9.8. Okay, 19. Yeah, I'm going to say 19.7. Okay, so my initial velocity, if I take that to the other side, it will be positive. So VI will be 19.7 meters per second. And please, guys, I want you to note this. They said I must calculate the velocity. Remember, velocity is a vector, so that means that this will be upwards. Okay, and note, my velocity came out as positive. It's showing me that it's going upwards because I've chosen up as positive. All right, I hope that's clear. Let's go to the next portion of this. They say, sketch the position versus time graph for the complete motion of the ball. Show the following on the ball, on the graph: the time taken by the ball to reach the ground, the time taken for the ball, by the ball rather, to reach the starting point, the initial and final position of the ball. Right, so here's what we are going to do, guys. I'm going to make an assumption. The examiner should have done so. Right, I'm going to take the ground as my zero position, meaning it means I'm measuring the position of the ball relative to the ground, right? So that means my graph is going to look like this. That's time in seconds. This is, okay, let's remove this calculator. This is position in meters. All right, and I want you to note in this case that when I look at my position, where if this is the ground, where did the ball start? It started 19.6 meters from the ground. And what happened? It went closer to the ground, right? And then went again far from the ground. So what does our position versus time graph look like? Okay, right, and oops, right, so this is going to be 19.6. Okay, right, remember it took 2 seconds to get to the ground, but it took an additional 2 seconds to go back to its maximum height again. So which means, so that's 2.01. That's going to be 4.02 seconds. Okay, so that is how our position versus time graph looks like. If you took time, or rather if you took, yeah, maybe some of you might want to ask, but what if I chose the top, the you know, whatever it is, the building as your reference point, right? What was our position time going to look like? Well, it's just going to be shifted in that case, right? Remember, it starts, let's assume that I'm standing here. So I'm seeing the ball start with me and it goes down, right? So which means your position versus time graph will start at 0 this time, go 19. So this is time in seconds. So this would be 0. This is what our position time graph would look like. So that's 2.01. That's 4.02. Okay, so this is if I took the position the top of the building or the top wherever it is that I threw this ball from, right, as my reference point. I wanted to show you quickly what would a velocity time graph look like. Okay, so the velocity time graph, I want you to keep in mind in this case it doesn't require us to specify relative to whatever, right? So I want you to think about it. What happened? We started from 0 and the ball went down, increasing in velocity, but we said down is negative, up is positive. So the velocity time graph is a straight line graph. So it would go into the negative direction. Our velocity at the ground was minus 19.7. Remember, we calculated it over there, right? But we didn't lose that velocity, right? Now I want you to note, it then changes direction very quickly. So you'll have this rapid change, right? This vertical line that shows you a rapid change in velocity. And now all of a sudden became positive, then it goes up, right? But as it goes up, it's losing that velocity until it becomes 0. It's losing that momentum. So this is going to be 4.02. This is 2.01. Okay, that's 19.7. This would be 19.7 over there. Remember to label your graph. So that's velocity in meters per second, and that would be time in seconds. All right. Okay, guys, I hope that was clear, right? Please, if there are any questions, you're welcome to throw in comments on the comment section. All right, we'll have a look at them and we will try to answer. I will give answers onto the comment sections for each and every one. Well, not each and every one of your questions because sometimes it's just comments. All right, but I'll try to answer each question as it comes. Right, so I wanted us to look at work, energy, and power. And guys, geez, man, when I looked at this question, there's a last part of it. I would advise on this question paper, I'll give you the link. You can find it on our Google Drive, right? I will advise that you go and look at question 4. It's just that I won't have any time, the time to look at it thoroughly as we go on with it. Okay, but I'm going to do question 5 with you. Right, let's quickly have a look at it. They say a diver of mass 80 kilograms. If you don't mind, can I just drink some water? All right. They say we've got a diver of mass 80 kilograms, steps off a diving board at A. So there's our diver there. Right, 4 meters above the level of the water of a swimming pool. The diver enters the water at point B and comes to rest. So I'm going to remember or remind myself that at C, my velocity is 0. Okay, right, and of course, when they were still diving, they started with an initial velocity of 0. Okay. Right, so they say to us, comes to rest at point C, while the diver falls through the air, an average frictional force of magnitude 172 newtons. Remember, that's the average frictional force in the air, right? Okay, they say the total work done on the diver while he moves from A till C is negative 6240. Now, let's quickly have a look at it. They say state the work energy theorem in words. So please remember your definitions. The work done on an object is equal to the change in kinetic energy. All right, so for 5.2, they say use the work energy theorem to calculate the speed of the diver at point B. Right, so we're looking from A till B. Okay, maybe let me just go on to this side. There's a little bit more space there. Okay, so we're looking from A till B. Right, think about it. What are the forces acting on the diver? Gravitational forces pulling this guy down, but we also have the frictional force, air friction. Remember they said to us it's 172, right? Remember friction opposes motion, So that means that we're going to take that frictional force to be 172. All right, so there's our gravitational force there. And we can find that gravitational force. That's 80 times 9.8. In fact, I can leave it as that. That's 784. 784 newtons. All right, so I'm going to say the net work done is equal to the change in kinetic energy, right? Now, please, I want you to note, guys. So I know how to calculate net work done because that would be the net force multiplied by delta x, the cos of theta, okay? And this would be equal to a half times the mass, okay, sorry a bit, half times the mass, Vf squared minus Vi squared. You could have used work done by non-conservative forces, and your only conservative force in this case, non-conservative force rather, would be the air friction, okay? So that would have worked as well. Right, so let's go for it. So we've got F net. That's going to be the gravitational force minus friction. Now remember, we take the direction of motion as positive. So that's going to be Fg minus friction. That's our F net times 4. Sorry, times 4. The cos of. Now remember, in this case, because my gravitational force, I can already see that my gravitational force will be much higher than the frictional force. It means the net force is the one that's pulling down, okay? So I want you to please consider what is the angle between direction of motion and the force, the net force in question. That would be 0, right? So that means at 784, that's what we got, right? Minus that frictional force, that's 172, okay, multiplied by 4, the cos of 0, and this is equal to a half of 80. Our final velocity is what we're looking for, the velocity at B. Our initial velocity at A was 0. Okay, so let's do some gymnastics. Okay, where's my calculator? Right, I've got 784 minus 172 times 4. Cos of 0 is 1. Okay. So I get 2448. Half of 80 is 40 VB squared. So I'm going to divide by 40 on either side. Okay, and take the square root. And I get VB to be 7.82 meters per second. Right, so please check that velocity. So now we know the velocity at B, right? So we're going to now look at the next question. So they wanted the velocity at B when the diver is entering the water, right? Now they're asking us, is mechanical energy of the diver conserved? Answer yes or no. Give a reason for the answer. Right, so definitely it is not conserved. Why? Because of the presence of non-conservative forces, or you can say because of the presence of frictional force. Okay, now in the next question, they say using principles, this is the question I was referring to. They say using principles, energy principles only, calculate the distance between B and C. Right, so we want this distance. Now, you need to keep in mind they had told us that the total energy, right, total work done for the diver from A till C, which means we're looking at it from the moment they left the diving board until they got to the bottom of the water, right? That was given to us as negative 6240, right? Now, I'm going to say the work done by non-conservative forces, right, would be equal to the change in kinetic energy plus the change in potential energy. Right, I want you guys to stay with me on this one. Right, so we're looking at the total work done. Okay, so in this case, I looked at it as the net, not the network done rather, but as the work done by non-conservative forces, right? Because that would constitute the total work done between those 2 points. So that would be minus 62, they said 6240. The change in kinetic energy, that's half multiplied by 80. Sorry, I was supposed to write down the formula. But what is our final velocity? That's 0, right? That's when we got to the very bottom. But what's our initial velocity? Our initial velocity is 0. Okay? Right. Remember, I am taking from position A all the way till position C. Plus. So that's mg. What is my final height? When I get right to the bottom, my final height is 0, right? Minus, what was my initial height, right? And I'm talking about the height relative to the bottom of the of the pool or whatever it is, right? So my final height was 0. My initial height, right from the top at A, that's 4 plus D, okay? So minus 4 plus D. That was my initial. All right, so let's do a lot of gymnastics there. So that's minus 6240. mg, that's mass, that's 80 times 9.8. But this is going to be, if I consider that negative in there, it makes this entire term be negative. So that would be 4 plus D. Okay, so what I'm going to do, guys, is I'm going to divide by negative 80 times 9.8. Okay, so that's 784 or 782. 6240 divide by, or we can say 6240 over 80 times 9.8. Okay, and I get 7.96, but remember I still need to subtract that 4, so 4 plus D would be 7.96, and taking this to the other side, D, that's minus 4, that will be 3.96 meters. All right, so which means our pool is 3.96 meters. Right, guys, I think this question, to be honest with you, in the way in which it was phrased, can be somewhat a little bit confusing. I tried it in a different way, and I must admit that it became a little bit challenging. I did it on a live that I did, yesterday, and somehow it just wasn't working out as much as I wanted it to. But this is how you'd go about doing that question. Of course, there are other ways, but I will not discuss that now for the purpose of wanting to conclude this live, so that at least you've got as much as you possibly can for tomorrow when you write that exam, or whenever it is that you will be writing that exam. As I did say, I'm still going to give you some advice on how you are going to do the other sections. Right, now let's go on to the electricity part. Right, I'm going to conclude on this. Right, that will be the last part that I am doing with you. So they say to us, we've got 3 identical light bulbs, which are A, B, and C, each with a resistance of 8 ohms. I'm going to put that there. And I've got 8 ohms, right? They're connected to a battery with EMF of 12 and an unknown internal resistance, as shown in the circuit diagram below. The resistance of the connecting wires and the emitter may be ignored, right? So, they say switch S is closed. So remember, the moment that we close the switch, okay, that means that our circuit is going to behave differently than it did before, right? So let's check. With the switch closed, we've got total current moving through the emitter, right? So there's our total current. Until it gets to this node, what happens when it gets there? The current divides. So some of the current will go through resistor or light bulb C, but some of the current would go through A and B. Okay, so there it is there. But what happens thereafter? Right, the 2 currents will meet at this node, and you've got the total current yet again going through your internal resistance and back again. Right, so that means, can you see, we've got different currents that are going through A and B. So A and B have got the same current. It's the green current. Let's call that I2. C has got its own current. Let's call it I1. Both I1 and I2 give us the red current, which is the total current. Okay. Now they say the switch is closed. The emitter reading is 2 amperes, meaning the red current would be 2 amperes. That's the total current in your circuit. So they say to us, define the term electrical power in words, right? Remember, power is the rate at which electrical work is done, or you can say it is the work at it is the rate rather at which work is done. All right, now let's look at the next part. They say calculate the reading on the voltmeter. So when I look at that voltmeter, this voltmeter measures across my parallel resistors. Okay? So you can look at it as a voltmeter that's measuring across my parallel resistors. But you can also say that it's measuring across the battery. So that gives you the external voltage. Okay? It's measuring across all the resistors in your battery. Right, so how are we going to get that? So firstly, we've got total current. Well, we can find out what the effective resistance in parallel is. So you can look at those 2 resistors, A and B, as just one resistor, which has a resistance of 16 ohms. Remember, A and B are in series. So when I add them together, I'm going to get that 16. And they are in parallel with each other. They are in parallel with resistor C, which is 8 ohms. All right. And so I will say, well, R parallel in that case, or RP, you can say product over sum, or you can take 1 over R parallel, 1 over R1. So I'll say R series times RC divided by R series plus RC. So that's 16 times 8 divided by 16 plus 8. Right, so we get a value of 5.33. Now remember, once I've taken all of those resistors and made them into one, right, which current is now going to pass through? It's no longer going to be I1 or I2 because they're now one resistance, right? The current that will pass through them will be the total current. So in that case, it means if I'm going to get V external, the value of V, that's going to be I total multiplied by R external. Right, for those of you that may be struggling with this section, please do watch my series, or rather the playlist that I've compiled on electrical circuits. What I've done, guys, is that I've started them all the way from grade 10 so that you can build up, so that you just don't land into now all of a sudden there's all types of resistors. So how I started is I started you on parallel resistors, on series resistors, and then I start combining them. Okay, right, so that will be 2 multiplied by 5.33, which gives me 10.66 volts. All right, so there we go. That would be the reading on the voltmeter. And then secondly, they say calculate the internal resistance of the battery. Now remember, we were given the EMF, okay? They said the EMF is 12, all right? So I'm going to say E is I into R plus small r. The moment they start talking about internal resistance, so I know I'm going to come back to this, okay? So that's 12 volts. Remember, this I that we use here is the total current, and our total is 2. That is R external, the total external resistance. That was, we found that to be 5.33 plus the value of R. Okay, so we're going to divide that by 2. That's going to be 6 is equals to 5.33 plus resistor R. And so R would be 0.67 ohms. Right, and that is how the cookie crumbles on that question. Right, so let's go on to the next portion. So we got the internal resistance. Now they say to us, compare the brightness of the light bulbs A, B, and C. Justify the answer. Right, now I want you to please notice a light bulb A and B have the same current I2 passing through them. It's that green current, right? So what can I say? A and B, okay, so A and B burn equally bright. Okay, and why is that? Because the same current passes through them. Okay, so they've got the same current passing through them, but they also have the equal resistance, right? Okay, so we know P, right? The moment they talk about brightness, guys, remember it has to do with power, right? So P is equals to I squared times R. So they've got equal currents, the same current rather, and they've got equal resistors, right? So in that case, that's why they will burn the same. However, C burns brighter. Now, let's talk. Remember, the moment that you look at these, you've got two resistors which are 16 ohms, right, together. So remember that more current goes where there is less resistance. So I'm likely to see more current going through resistor C because it has less resistance, right, than A and B together. So more current will pass through there. So I said C burns brighter than A and B due to more current passing through. All right, guys, I hope that makes sense. All right, and we are almost at the end. Okay, so they say to us, and please look out for that advice that I'm going to give you right at the end. They say the final question, they say switch S is now opened. Now what's going to happen when we open switch S? Okay, can I just remove all of the stuff here? Okay, so let's make it less confusing. So the moment I open switch S, right, there's no longer any current that is flowing through resistor C, right, or light bulb C. So which means we've killed that light bulb. So meaning all of your current will now go through A and B only. Now I want you to please also remember this. The moment you remove a resistor in parallel, it means your effective resistance, your total resistance will actually increase. Okay, right. Now, I want you to note in the you note this. If you were to measure the R external, now it will be 8 plus 8, which is 16, whereas at first, we found the effective to be only 5.33. So it shows you that R external has actually increased. Okay. Right, now they want to know the following. They say, how would the voltmeter reading change? Choose increase, decrease, or remain the same. And they say, explain the answer. Okay, right. Now I want you guys to remember, whatever happens to R external will happen to V external. When we measured that voltage, we realized it was V external. So because R external will increase, remember I started for 5.33 initially when the switch was closed, and now it's 18 ohms. So which means R external has increased. So which means we can say our option there is increases. Remember guys, positive marking, or rather negative marking, applies here. Which means if I don't get the first answer right, the first choice, increase, decrease, or remains the same right, everything else that follows thereafter will be marked incorrectly. Okay, right. So it will increase. That's what we said. Okay, and let's explain. So firstly, R external has increased. Okay. So R external increases, but an increase in R external will decrease the current. I is equal to V over R. When I increase resistance, the current decreases. Okay, right. And then we know that V internal is I multiplied by R. But remember that small r remains the same, remains constant. Okay. Then, therefore, we can conclude that therefore V external plus V internal is equal to the EMF. In fact, let me write this properly. So E is equals to V external plus V internal. But what do we note? V internal has decreased. E stays constant. The EMF doesn't change. So two things that don't change, that's the EMF and the internal resistance. So if the EMF stays constant and I decrease internal voltage, then what will happen to V external? V external has to increase. Right, guys, because of time, I won't necessarily delve too deep into this. I've covered it in my section for electric circuits. I hope that you've been able to watch that. But if you haven't, please just make sure that you can watch that. And it's really, really for me important for us to revise when it comes to physics. Those questions have been coming thick and fast, and they are really upping the standard in terms of how they question on these sections, right? So what I do want to say in conclusion, guys, as I leave it here, I want to say to you, firstly, I want to wish you all of God's best as you are going to write. But for those of you that may have been struggling with physics, for those of you that really have been struggling with mental issues, throughout the year, because I understand that the matric year can be really, really challenging, guys. I want to say to you, please hold on, okay? There's no reason for you to lose hope. NgesiZulu, we usually say, "Akulahlwa mbeleko ngakufelwa." That means that you have to keep your hope up, right? Just because you've gone through a difficult time, it doesn't mean that you should cast all your hopes away. You should just throw in the towel, as they would say proverbially. I want to say to you guys, if you've been struggling, please, it's through no fault of your own. There are many options for you, right? You can still use the remainder of the year. By the way, we're still going to have some sessions, right, during our school holidays, right, where I will take you through master classes, right? I've got a series of master classes that I'm going to do on each section. So you can go to the master class that you want. You can pick the one that you want. We will have the link live on Sunday, right? That's the one that you can pick. And then another thing is that you still have an opportunity to improve. But if you feel like, maybe that's a bit too much. Guys, I've got a group of learners that are upgrading at my center, and one of the things that we are realizing is the pressure that is there in the school system, and particularly that they place on the matric year, and there are so many gaps that are there. So you are not the problem, okay? Sometimes how the system is sometimes might give a little bit of an issue, but I don't want you to look at yourself and be despondent about your future. The Bible says, I like the book of Jeremiah 29 verse 11. It says, "For I know the plans that I have for you, says the Lord, plans to prosper you and to do you good." So I want you guys to really lean on that scripture and know that wherever you are in your life, God has a plan for your life. God has a plan and a purpose for your life, and His plan is to prosper you. Use this time to get yourself ready. Use all the resources and the opportunity that you have. But if things are not going your way, please, there is still a second chance. You can still come back and bounce back, just like that ball that we were looking at. Okay, so guys, it's really been a pleasure being with you. Thank you so much for granting me the opportunity, and I wish you all of God's best as you write. We will come back with graphics and the link on when our master classes will be. But from me for now, I'll see you guys again next time. Sharp, sharp.